entire week. So your assignment will not be due during spring break, okay? And I will be posting the work plan, guidelines, and template for that assignment that's due on the 28th, probably sometime today. I'm just going through and making sure I'm on typos. That's about it. And let's see what else. And that should be it for now in terms of the assignment. That was a grand announcement for that. Okay. Ratio. Back to lithium sulfur. I don't know if those of you who came in a little bit later, we started the discussion before class started about lithium sulfur crystallization. Well, and specifically the recrystallization of sulfur upon charge, and how you can actually have a coexistence of the crystallized state. You can have also the lithium polysulfides that have formed, and that will either crash out of solution, or if they're unconverted, then maybe they're still in the liquid state, or sorry, the dissolved state. And then also, depending on the metal of the substrate, the current collector, you can also recrystallize sulfur in the charged products, not only dendritically, but also how it coats the substrate again can be dictated by the metal of the current collector that you choose, or alloys, I should say. So that's what we were talking about, which then led me to the discussion with them. Right. So in terms of the context of where lithium sulfur is right now, and where it's going, is there's been quite a bit of fundamental studies already done, right, that we talked about encapsulation of sulfur, engineering the electrode to suppress the polysulfide shuttle, to also minimize the volume change, or at least deal with the volume changes better, because volume change is inevitable with lithium sulfur discharging and charging. And obviously you can control your electrochemical window so that you never go so low in the voltage during discharge that you reach Li2S. You can do all that. But you also limit your available capacity that you will choose. So all the engineering feats that have been summarized beautifully in this table here that I won't redraw, but I will cite, points to the fact that we understand the challenges of lithium sulfur, particularly from a small batch, small scale coin cell fabrication point of view. The push now is to engineer electrodes for pouch cells, larger cells where you're achieving higher capacities, and that we've discussed, amongst different material systems as well, that is not always a linear and direct translation. Okay, so that's where we left off. So where is the design going? Well, it goes back to what we talked about before here, that you want to have a lean operation, right, to maximize the energy density. And so to do that, you can decrease the electrolyte to sulfur ratio, right? Decrease so you're not drenching your cell anymore. And that does, for fixed sulfur loading, that does increase energy density. Now, you can also increase the sulfur loading to get higher active, higher sulfur utilization as well. But then after a while, it sort of plateaus. So it increases sharply, as you can see here in this model, but then it plateaus and then sort of decreases, which is not so obvious from this angle. So where do we need to be? What are our targets for engineering these types of electrodes? Where we need to be is basically at 400, 500 watt-hour kilogram to be competitive for electric vehicle applications. So what that really means is we need to be able to engineer electrodes that perform well, that cycle well, have high cyclability, high rate capability, and the mass loadings are relatively high. So these numbers are pretty typical: 5 milligrams of sulfur per centimeter squared of the electrode area, moving to 500, that's 6 milligrams per centimeter squared, and even leaner operations of electrolyte to sulfur ratio. So that's where we really need to be to be competitive. So, in going back to talking about how different are the operations and the engineering complexities going from coin cell to pouch cell, you see that already here. I think most of you are probably more familiar with the coin cell because most academic settings, you first start testing with coin cells before you move on to anything large, right? Before you move to advanced type cell design. And so, we're used to, at least for lithium sulfur, dealing with pretty drenched cells with greater than 10 microliter of electrolyte to per milligram of sulfur loading. But then when you move to, let's say, larger, and you can see here orders of magnitude more in terms of capacity, you could see that the electrolyte to sulfur loading ratio is much leaner, and you're increasing the sulfur area mass loading. So that this translates to a whole lot more occurrences of lithium polysulfide shuttling. This also encounters the problems that you wouldn't have had before, which is limited capacity because you just don't have enough electrolyte to really permeate the sulfur or the specialized carbon, order structures that you have. And so your capacity just drops way off because you're running so lean, right? So now you have to go to basically scaffolding design that would allow the diffusion of the liquid electrolyte more efficiently to get to the sulfur. So the materials design for, let's say, coin cell testing that you would not have had these issues before, now you have to actually solve them when going to pouch cells. Okay, so but supposedly you can. There is a commercial cell out there that one can buy to actually have these things. But anyway, but still behind on lithium-ion battery technology development. All right, so that caps the discussion of lithium sulfur for now. We will revisit some of this discussion when we talk about interfaces, although we'll talk about it in the context of actually solid electrolyte interfaces. So now we'll move on to a related topic to that of conversion materials, and that is alloy-based anode materials. So the natural discussion would be silicon, as it is state of the art, but we'll also talk about tin, as well as some of the more, I guess, I wouldn't say not as developed, but there are additional challenges to germanium that people have solved with silicon. Now, the motivation for why people have looked into, really trying to understand the mechanisms of lithiation and delithiation in these alloy-based materials is because of the high theoretical capacities, right? I don't think that's news to most of you. And we can see that. So if we, look at the theoretical capacities of silicon, we see that it ranks the highest of all the common-based alloys that are out there. Silicon versus germanium versus tin versus antimony. Now, this is based on how much lithium, the theoretical capacity, how much lithium you can get to alloy with that of the the anode. Of course, the concomitant issue that needs to be mitigated is, of course, the large volume change. So this is related to lithium sulfur for the same reason, is that upon alloying with lithium, the material undergoes huge volume changes. So you see 676 here for tin, you see a little bit less for that of silicon, and then germanium, a little bit less. Ideally, you would want smaller volume changes, but then you're left with also smaller values of, achievable theoretical capacity. So it's always an offset. Now, in terms of costs, we talked about this in the sustainability section, but to review, you see here a collection of the cost per kilogram of the raw material, and silicon ranks pretty high in terms of the lowest cost, right? So the motivations are there for studying silicon, as we know. So if we look at then the phase diagram to see what phases we can access, how many moles of lithium can we alloy with that of silicon, we see that in the thermodynamic equilibrium, the thermodynamic phase diagram for the bulk phases, we can achieve quite a number of these crystalline phases, right? And the ratio of this Li22 Si5, that's pretty high, right? That's 4+ moles, right? So that's pretty good, because compared to, let's say, graphite, you need 6 carbons for every 1 of lithium, right? So here, for every 1 silicon, you can convert 4 into the lithiated phase, or 4 mole equivalents of lithium. Okay, so that's pretty high. Now, what you have seen in terms of the theoretical capacities that have been reported, it's usually for the delithiated phase, right? So a review of the theoretical capacity and how we calculate that, right? So that's N, the number of moles of lithium, or equivalently moles of electrons times Faraday's constant, divided by the molecular weight of the active material. In this case, if we consider delithiated silicon, then we take into account that silicon's molar mass is 28.08 grams per mole, and that gets us the number that is 4,200 milliamp-hour per gram that you see cited quite often. So that's converting and alloying 22 lithium with 5 that of silicon. Okay, so that stoichiometry is taken into account there. But the reality is, if you think about the lithiated compound and you calculate the theoretical capacity based on the maximum number of lithium ions, which is Li22, Si5, the molar mass there is 293.13 grams per mole. So if we take that into consideration, the lithiated theoretical capacity, or I should say the theoretical capacity based on the lithiated compound, is actually 2,000 milliamp-hour per gram. Right. So there is a distinction on what you consider as your active material. So the number that you see that's cited often is referring to the delithiated phase. Okay. Now, in terms of what should we expect, when we approach this problem in terms of materials design, right? We expect, looking at the phase diagram, that there's potential to crystallize in a number of line compounds, right? So we can expect perhaps lithiation to form this 1-to-1 compound, 12-to-7, 7-to-3, 13-to-4, 22-to-5. These are the phases that we potentially could expect, even though electrochemistry is a non-equilibrium technique, right? So one of the first studies that were done in the 70s, in 1976, by this group, looked at just that lithiation and delithiation. And at 400, well, in a eutectic, so at 407 C, and why 407 C? That's because that's the molten state. So that's the eutectic point right there. So at this particular composition of lithium chloride to potassium chloride, at 407 C or 680 Kelvin, you're in the molten state. And you can see at elevated temperature, the discharge profile or the lithiation profile of silicon in this eutectic electrolyte is exactly what you're expecting. You see a two-phase coexistence, and then you form the next compound, and then you form the next compound, so forth. So you form those phases that you would expect from the phase diagram. So which is pretty, promising and as expected. But I'm showing you this to contrast with that of what is to come, which is the unexpected metastable phases. Okay. So the unexpected metastable phases arise from the fact that the materials that perform the best are nanostructured. And so when you're in the nano regime, you now have kinetically stabilized formation of metastable phases that you would not normally get in the voltage or at elevated temperatures. So now you could also potentially be dealing with metastable phases that form from amorphization of the alloy. So, but what you see here is if you just start cycling lithium, right, you bring it down to now room temperature instead of that elevated molten salt battery, you bring it down to lower temperature, and what you see is instead of very well defined plateaus that you see here, you see something that looks like this. Okay. Now, I note this figure because here the denotation for alloy, which is lithiation, is actually charging, and that's flipped from what we usually refer to as discharging. Okay. So I'll be more specific and talk about and use the terminology of lithiation and or delithiation so that there's no confusion. Okay. I'll also use the term working electrode and counter electrode as well. Okay. So that it's very obvious what is the active material. But here in this particular example, there's 10 micron silicon powder, some conductive carbon, some binder in a weight percent distribution that is pretty within the realm of conventional composite fabrication. And what you see is there's dramatic capacity fade for these larger size, larger relative to what is state of the art, which is nano. So larger size silicon powders, there's irreversible capacity, as you can see. So you lose a lot of this capacity that you don't regain. So here's the lithiation, here's delithiation. So you lose quite a bit of capacity. So there's greater than 50% capacity fade. And what happens here in these micron-sized particles is that once lithium comes in during lithiation, they sort of get trapped there and they don't come back. So that's what you see, that your second lithiation cycle, you start off with what you left off with for a delithiation in the first cycle, and then you basically just start to gradually lose active material. Okay, so there are trapped lithium ions within the silicon matrix, and you form whatever phase that you form, and they're not being released back during the delithiation phase. So then the strategy for designing is, okay, let's move to smaller particle size. And that's motivated by the fact that we just saw the electrochemistry, is not promising in the sense that the capacity fade is high, right? You have trapped lithium ions, which you don't want. And on top of that, the mechanical integrity of your electrode fades rapidly. So this has been seen with a number of thin film studies. So you see that here, that you have a thin film of silicon, and upon lithiation and delithiation, you basically introduce cracks, and that's what you see. This other study that performed in situ atomic force microscopy, or AFM, what you see is the same thing, but they map out, during lithiation, delithiation, the same phenomena that you see, which is cracks. And just for funsies, this is the salt flats It's called the racetrack in Death Valley. Yours truly took that photo, so I cited myself. I do have a hobby of camping in the winter time in the desert because, you know, I enjoy suffering. But anyway, so you can see the large volume changes contribute to the mechanical fractures that are observed through the various microscopy characterization techniques. And so in terms of these phases that are reported, you know, you can see not only are there large volume changes between, you know, the N compound versus silicon, but it goes through quite a number of changes, you know, through the intermediate line compounds as well. Now, when you move to nanostructured silicon, what's interesting is you now have kinetic issues to deal with. And what is observed actually is that there is a formation during lithiation. When you start off even with crystalline nanostructured silicon, you form intermediate lithiated silicon phase that's amorphous. And that results in the formation of this metastable Li15S4 crystalline phase. And you can see that in titanium, and this has been established for about 9 years now, that this, well, actually more than that if you include the work of the non-in situ characterization work from 2007 from Oberbach. Okay, so the fact that it's nanostructured, there's a different pathway than just going from crystalline silicon to then the crystalline compound, but it stabilizes metastable phase. So how does that actually work? And what now is the new phase diagram? The phases that one anticipate. So what you see here is a quite different voltage profile than what I showed you for the molten electrolyte, right? Where you were expecting stepwise plateaus, indicating that you're forming these crystalline phases from the phase diagram. What you see here more is what one could consider sloping, you know, plateau-ish, but mostly sloping. And then here in subsequent cycles, you see really sloping. So now it's indicative that you're forming a single phase intermediate and that you're not going through a two-phase region. Okay. So what's been proposed based on characterization is, and the electrochemistry as well, is that you're forming starting with silicon in this one phase to that of this amorphous Li-Y Si phase. Okay, and then from there, what will form is at the end here, this point 2, you're forming from the amorphous lithiated silicon to that of the metastable Li15S4. So that's the first discharge that you see. And then from there, you're starting from some amorphous phase. You're now delithiating, and you still have this Li15S4, but you undergo this amorphous transition. So you go back through the amorphous region. And then you start off with amorphous lithiated silicon. And by this region, this discharge secondary, you form or you reform LIX Si. And the X is, of course, dependent on where you are along the discharge and how much you're lithiating. Okay. And then subsequently, you know, you form these different amorphous phases. Okay. Now, in terms of, you know, realizing that nanodispersed silicon can also achieve higher capacity, that's been well understood since, you know, the mid-90s by Jeff Don's group. But really, we've gotten better at processing silicon so that we can stabilize these anodes over hundreds and thousands of cycles. Okay, and that is due to the fact that we can now have lithographic designs where we can grow silicon nanowires in an oriented direction and increase the efficiency of electron transport. Okay. So silicon now, in this particular design, in this fabulous paper in 2008 by Candace Chan, that they can deposit through VLS, so vapor liquid solid growth. You start off with gold catalysts on the substrate, and then through introducing silicon vapor precursor, and then having it grown onto the substrate, you can grow these silicon nanowires and directly have it be in contact with the current collector. Okay, so that's a shift in design. And why this was looked at is because the nanostructure will help you avoid pulverization that's been observed for larger size particles, like the micro-sized particles that we just talked about. Now, what is acknowledged is, of course, you might have a little bit of reduced capacity because there's some phase inferiority. In fact, 0.25 phase fraction, so 25% of your material is this alpha iron silicide, but the other 75% is the silicon that you're desiring to grow. And what's also really good about this material in terms of the advantages is that there's strain relaxation along the growth direction that survives the expansion and contraction over thousands of cycles. Okay. And on top of that, and this is a theme that we'll revisit, is the issue of the binder, right? If you have your active materials in particle form, what you need now is to make a composite where you have continuity, right? You need to have your active material, that's silicon or sulfur, that's electronically insulating, be in contact with that of a conductive carbon, and then all of that needs to be bound together via a polymeric binder, which all, at the end of the day, adds weight to your electrode design, right? And eventually your cell. That's no surprise there. So one, you can try to decrease the amount of carbon that you have, but then you suffer the consequence of decreased electronic conductivity. Or you can try to get rid of binder materials by designing through lithography these nanowire, nanorod type of design. And so by these are all the strategies that folks often play around with when it comes to trying to increase the capacity. So what you see here for these nanowires is sort of the same, right? You don't see in the voltage profile, you don't see the plateaus that are expected for the bulk structure. You see this sort of sloping feature that's indicative of a single phase. So that once again, it confirms that you're going to this amorphous region, single phase region of growth for lithiation and delithiation. What you also see here, wild cycled at C/20, which is pretty slow, but what you see is the achievement of extremely high capacity. Okay, the 4,000 milliamp hour per gram that you expect, and then as you increase the rate capability, the efficiency of diffusion decreases, and you don't achieve as much capacity, but still pretty competitive. 2,000 milliamp hour per gram is nothing to sneeze at, of course. So promising, even though this is a fundamental study, a demonstration of silicon nanowire growth. Okay, so now, once again, this is 4,200 milliamp hour per gram. So I just want to note that this is now, you're operating below 0.5, 0.05, sorry, 50 millivolt versus lithium plus. And that's where you typically see the Li15 Si4 phase forming. So, well, so that's that's a quirk in the system. Now, in terms of statistical representation, how many of these silicon nanowires were really investigated? Well, in terms of the count, so number of nanowires, as you see here, for counting the number of nanowires that were actually looked at, they're in about a few hundred, so good enough. That's not 10, but it's not 2,000, so
it's sufficient enough for us to try to understand what is happening in the system. Is this representative, or is this one fabulous nanowire that was created? And in terms of trying to understand also the phase transformation within these nanowires, we can also do just regular, resistance measurements, and just look at, well, here it's not your typical 2-point probe. Well, it is, but at the MEMS level type of device level. And what we can see is before cycling, here you see the diameter is 89 nanometers plus or minus 45. So this dispersion in terms of how controlled these nanowire sizes are is pretty large. But after cycling, what you see is the nanowire diameter increases quite a bit. So either there's lithiated phases that are trapped in there or what have you, but certainly there is some transformation that is not reversible, and thus contributes to the capacity fade that you see. Okay, but still a fantastic demonstration of nanowire growth and also usage in improving the electrochemical performance of silicon at the nanoscale. Now, there's also, since this work, there's also been quite a bit of studies that have been done to really try to understand how lithiation occurs within these nanostructures. Right? Is it an instantaneous nucleation? How does the growth direction, the lithiation, the lithiating phase, how does that grow, along the wire? Because that will also help us design the growth direction for subsequent samples, right? So what you see is you can grow single crystalline, silicon, but as soon as you start lithiating and cycling, what you see is the formation of this amorphous lithiated phase, and then you see the formation still of the amorphous phase, but then the crystalline formation of LiX. So the fact that you can form crystalline Li15S4 within these nanowires, you can detect that. So you can see how it nucleates within the middle of the nanowire. Okay. And then here at 10 millivolts versus lithium plus, you could see that basically the entire nanowire is amorphous. So that goes to show you that at the nanoscale, what's happening is that the fact that silicon nanowires are undergoing this amorphous transition, it's stabilizing the kinetically induced lithium-15 Si4 phase that you would normally get under thermodynamic equilibrium in the bulk phase. And thus you never actually get to Li22 Si5. I think I've been saying S. I need to say Si. No, I didn't need to say sulfur. I've been needing to say silicon. So that's dramatically different phase transformation than what is expected in the bulk. Okay. Now, the arc of history is long and it often curves back. So now we revisit micron-sized silicon for the same reason that we want to decrease the usage of binders and conductive carbon. So there's more recent work. So that work was from 2008. There's more recent work just from, that was published last year, which means they've been working on it for much longer than that. But what you see is a demonstration now going to an all solid cell, the utility of micro-sized silicon that you normally wouldn't expect to cycle as well. And one of the reasons why we can come back to micron-sized silicon anodes is that instead of liquid electrolyte, so before all the systems that I was talking about for the micron-sized powder of silicon interacted with liquid electrolyte. And during the pulverization step, what happens is the cracks form, and then you have now new surfaces where the solid electrolyte interfaces can form.
Now, these SEI are not always advantageous for the cracked material. And on top of that, if you have a lot of cracking and pulverization, what's happening is now you're having more, delamination, physical changes in your electrode material. You have delamination off of the current collector, so now you have less of electronic conductivity. And on top of that, the SEI can also contribute to the isolation, the electrical conductivity of your entire composite. So not only is your electrode going through just physical changes, being pulverized, but the SEI contributes to further isolation of your electrode material. Now, that's the case for liquid electrolyte. For solid electrolyte, you can now go back and then you don't have the same challenges as you did with liquid electrolyte. So that's what they demonstrated here for this full cell, where you have micron-sized silicon, and then you have some naturally forming passivating interface with 700 micron thick Li6 PS5 chloride solid electrolyte. And then you have an NMC 811 cathode, although this has been protected with boron. So it's not uncoated, which is a whole different ball game as well, which we'll talk about when we talk about in 2 weeks, electrode-electrolyte interfaces. But the NMC 811 is protected with boron-based coating. And so what you see is that under these testing conditions, in pretty extreme temperatures, so negative 20 degrees Celsius all the way up to 80 degrees Celsius, you can achieve pretty high full cell capacity that is much higher than typical lithium ion battery capacities. Okay, so why do you want to reduce carbon additives, right? I mean, they're pretty good for what they do, right? They're lightweight, pretty inexpensive, and adds electrical conductivity pretty easily, right? Extremely good for that reason. And one of the reasons why you would want to do that is if you look here at the cell voltage curve versus capacity, you see that carbon can actually induce some decomposition. And this is what I've seen in other areas as well. You work with, let's say, other types of ceramic materials with carbon additives. You can actually induce a side reaction with carbon that might not normally occur. Okay, so and on top of that, reducing additives, period, will also decrease the weight of your cell. Okay, so and thus increases your potential for higher capacity. Okay, and also now you don't have to deal with interfaces, additional interfaces. The cathode or the anode to the conductive carbon interface. Now, in terms of testing these current density and rate capability, and then also stability at lower temperatures, and also higher areal loading of micron-sized silicon, what they've done is they perform all these tests, and these micron-sized silicon samples, electrode composites, perform pretty well. So you can see here, in terms of the capacity test, the current density test at room temperature, while there is a fade going to higher capacity, it's still performing pretty well, achieving in the thousands of milliamp hour per gram. And then in terms of stability at low temperatures, it also retains high performance at high C rates. And then as you increase the mass loading of silicon, it can also maintain, well, although this is at 60 degrees Celsius, it can also maintain high electrochemical performance. So in terms of a processing perspective, this is pretty attractive because one, now you can go back and use micron-sized silicon that you weren't able to before, and that's because you switched over to solid electrolyte. Okay. So that's really exciting because as you've seen in our discussion of the nanostructured silicon before. Typically, the production of nanostructured materials is more costly. You know, the design is a little bit more involved, and there isn't always a top-down approach to the production of nanostructured materials. Typically, it's, you know, by design, you have to go from bottom up. And what I mean by that is you can't just start off with bulk materials and try to basically pulverize it or ball mill it until you get some really, really small nanostructured design, right? Sometimes, just like the DLS, you have to go bottom up and grow your nanostructure as opposed to just, you know, starting with something big and then getting it to a smaller size, right? So the synthetic design for nanostructured materials sometimes makes the manufacturing process more costly. So the fact that, you know, you can now utilize potentially, you know, micron-sized silicon that you can buy, you know, from a commercial vendor is pretty attractive. But this came out last year, so, you know, it's all quite nascent. And in terms of some of the other pertinent electrochemical performance, you can see here for the full cell, the average coulombic efficiency is pretty high, right? So when I say pretty high, I mean 99.9 is pretty good, 99.95 is very good. So that's promising. And, you know, every decimal point matters. So here's a perspective. You know, if you have 99.98 versus 99.9, right? If you lose even 0.08%, you could see the dramatic decrease in the capacity retention in just going from 0.08 decimal places difference, right? So 99.95 is extremely promising for a first demonstration of this type of cell, you know, from a lab point of view. Okay. So, and the last bit of conversion-based material, I'm going to jump ship from silicon over to that some of the other alloys that we haven't talked about yet, which are tin and antimony. And I selected this system over germanium because germanium, you know, there are some analogs and some similarities to that of silicon. And I wanted to focus on these heavier elements because they are attractive in the sense that they have the same advantages. The theoretical capacities are higher, but the volume changes are also, you know, large, but they're sort of like in the middle, you know. So what people have tried to do is try to make these mixed phase alloy anodes to sort of utilize the advantages of the properties of each of the components. So what people have tried to do for this, you know, the same motivation is to minimize the pulverization. But here, instead of just nanostructuring, although that is also a typical technique in all of these materials, you'll find a lot of literature on tin, on antimony, but specifically mixing this the two phases together accesses the properties, the inherent properties of the different materials. So what you want to do in terms of absorbing these large volume changes that your anode material is going to experience is basically try to have one component be more reactive. And you limit the electrochemical window so that you can only lithiate and access one material and not the other material, because the other material will inherently have to lithiate, you're in a different part of the electrochemical window. And so you're basically trying to limit what phases you form. And so the example for tin and antimony is that by mixing the two together and forming this alloy, tin antimony 1-to-1, is that you have a metallic matrix that will allow the active phase material to expand within an unreactive ductile material or ductile matrix. So what that means is this matrix that's going to be unreactive because you're just not accessing that material because you're outside of the electrochemical range for that. what you can do then is the ductile matrix will absorb better because it's more ductile. You know, it can withstand the strain more of the large volume changes, while allowing the active material to undergo lithiation and delithiation. Right. So that's all summarized here. Right. So that's so you have tin antimony in a matrix of tin. So tin is the more ductile material. Okay. Oh, sorry, that's a typo. Tin should be more ductile. So if you look at then the phase diagrams, because we love to look at phase diagrams. If you look at the phase diagram here of the lithiated phases, you could see, well, tin, you can lithiate more, right? You can form this lithium 17 tin 4 compound, whereas for the antimony, you can get a 3 to 1, so a little bit slightly less than the 4. Okay, the 4 lithium ratio to that of tin versus 3 lithium to that of antimony. Okay, so the phase diagram is much more complex for tin than that of antimony. And so if you look at the end members, what you see is if you only lithiate tin or only lithiate antimony, what you see is exactly what mirrors that of the sort of expected phases for the phase diagram. You see here, the two-phase coexistence, these plateau regions, and in antimony, you see exactly that, the formation of Li3 and antimony 1. Okay, so that's for the end members. Now, if you then start mixing this sort of two-phase composite region, what you get is, let's say, this tin antimony, what you get is increased capacity in the two-phase mix composite versus the end member. So you can see here on the x-axis, there is the cycle number and the capacity retention is on the y-axis. So you can retain the same amount of capacity, but for over larger number of cycles. Okay. And so what you can do is restrict the electrochemical window here where you can form Li3 antimony, but then if you go below, let's say, 0.6 volts versus lithium, if you avoid that, then you prevent further lithiation of tin. So basically just limit the electrochemical window so that you only access that of antimony, so that your tin matrix can remain tin and just absorb and be ductile and absorb all that volume change, okay, for lithiation and delithiation. Okay. So that's what's been demonstrated. In terms of capacity retention, all these examples basically show that, when you have this two-phase mixtures, you have increased capacity retention, you have increased capacity, initial capacity, and then you can get really, complex with all these designs. You can also introduce like core shell type structures. You can also introduce nanostructures with voids, so that any growth of the lithiated phase will grow into these voids and be encapsulated in these voids, so as to not polarize and rupture your electrode, which is also the strategy for all the other anodes that we've already talked about. Okay, so still ongoing work in terms of where these alloys can go, and in terms of sustainability. There are arguments for using tin over that of germanium, but really the focus has been on silicon for all of the advantages that we just talked about, which is the earth abundance, the cost, and also the high theoretical capacities that one can achieve. But that's not to say that we should stop working on really trying to understand these composite designs, because then they can also, the foundational knowledge that we can establish with these composites can relay that and provide us feedback loop for how we think about design of silicon and other nanostructures. Okay, so this concludes our discussion of alloy anode materials, and we're going to continue after spring break the discussion of electrolyte interfaces, because that is the frontier.